Here is a fact that should genuinely disturb you. Everything you have ever seen in your entire life, every star, every planet, every galaxy, every person, every atom, every single thing you have ever looked at or touched or thought about, all of it represents approximately 5% of everything that exists in the universe. 5%. The other 95% is something else entirely. Something we cannot see. Something we cannot touch. Something we cannot detect directly with any instrument humanity has ever built. And yet without it, none of what we can see would exist at all. The galaxies would have torn themselves apart billions of years ago. The stars would never have formed. The planets would never have coalesced. Life would never have emerged. You would not be here. 27% of the universe is made of something called dark matter, an invisible, undetectable substance that holds the entire visible universe together like an enormous cosmic skeleton that we can only infer exists by watching what it does to everything around it. We have known it is there for nearly a century. We still have absolutely no idea what it is. To understand dark matter properly, you have to go back to the 1970s. And you have to meet Vera Rubin. Vera Rubin was an astronomer who spent years doing something that most of her colleagues considered almost embarrassingly mundane. She measured how fast galaxies rotate. Specifically, she was interested in spiral galaxies, the pinwheel-shaped structures like our own Milky Way, and she wanted to know how fast the stars at different distances from the center were orbiting around it. The answer everyone expected was obvious. It was the same answer Newton gave us centuries ago and the same answer that works perfectly for our own solar system. Objects closer to the center of a gravitational system move faster. Objects further away move slower. Mercury, the closest planet to our Sun, orbits at 47 kilometers per second. Neptune, the furthest major planet, crawls along at just 5.4 kilometers per second. The math is clean. The physics is settled. This is not complicated, except when Vera Rubin measured the rotation of galaxies, she found something that should have been impossible. The stars at the outer edges of galaxies were not moving slower than the stars near the center. They were moving at roughly the same speed. In some cases, the outer stars were moving just as fast as the inner ones regardless of how far they were from the galactic center. This violated everything we thought we understood about gravity and mass and orbital mechanics. If you applied standard Newtonian physics to these observations, the outer stars of most galaxies are moving so fast that the visible mass of the galaxy simply cannot provide enough gravity to hold them in. They should be flying off into intergalactic space. They are not flying off. They are staying in orbit, moving at speeds that make no sense given only the mass we can see, which means there is mass we cannot see. A lot of it. Vera Rubin did not discover this anomaly alone. Fritz Zwicky had noticed something similar in galaxy clusters decades earlier. But it was Rubin's systematic, meticulous, undeniable observational data that finally forced the scientific community to take the problem seriously. The conclusion she reached was straightforward even if the implications were not. There is more matter in these galaxies than we can account for with visible stars and gas. Something invisible is providing the extra gravitational pull that keeps those outer stars in orbit. She called it the missing mass problem. We now call it dark matter. And in the 50 years since her work, the evidence has only grown more overwhelming and more mysterious. Vera Rubin's galactic rotation curves were just the beginning. In the decades since her observations, astronomers have found evidence for dark matter coming from multiple completely independent directions. And this is important. It is easy to dismiss one anomalous observation as a measurement error or a gap in our understanding. It is much harder to dismiss 5 separate lines of evidence all pointing to the same conclusion from completely different angles. The bullet cluster. Perhaps the most visually striking evidence for dark matter comes from an object called the Bullet Cluster, two galaxy clusters that collided approximately 150 million years ago. When these two enormous structures crashed into each other, the visible matter, the hot gas that makes up most of the ordinary mass of galaxy clusters, slowed down during the collision because ordinary matter interacts with itself. It collides. It heats up. It creates shock waves. But something else did not slow down. Astronomers mapped the gravitational mass of the system using a technique called gravitational lensing, which I will explain in a moment, and found that the majority of the mass passed straight through the collision without slowing down at all, as if it was not affected by the impact, as if it barely interacted with anything. The ordinary matter and the gravitational mass separated during the collision. The visible hot gas ended up in the middle, the characteristic bullet shape that gives the cluster its name. The gravitational mass, the dark matter, kept moving and ended up on the outside. This is one of the cleanest, most direct pieces of evidence we have that dark matter is a real physical substance separate from ordinary matter, not just a flaw in our understanding of gravity. Gravitational lensing. Einstein's general theory of relativity tells us that mass warps the fabric of spacetime, and when light travels through warped spacetime, it bends. This means that a massive object, like a galaxy cluster, sitting between us and a more distant object will act like a cosmic lens, bending and distorting the light from behind it into arcs, rings, and multiple images. The degree of bending tells us how much mass is doing the lensing. And consistently, systematically, without exception, the mass required to produce the observed lensing effects is far greater than the mass we can account for with visible matter alone. Sometimes 5 times greater, sometimes 10 times greater. The universe is bending light with gravitational fields that are far too strong to be produced by the matter we can see. Something invisible is doing the bending. The cosmic microwave background. When we look at the oldest light in the universe, the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, we see a pattern of tiny temperature fluctuations that encodes the conditions of the early universe. The precise pattern of those fluctuations, their size, their distribution, their amplitude, is exquisitely sensitive to the composition of the universe. When cosmologists model the early universe and try to reproduce the observed pattern using only ordinary matter, they cannot do it. The pattern only fits the observations when you add dark matter into the equations. Specifically, approximately 5 times as much dark matter as ordinary matter. This is not a fudge factor. This is not scientists adding an invisible ingredient to make the numbers work. This is the universe's earliest light telling us directly what the universe was made of at the very beginning. And it says, most of the matter in the universe is something we have never directly detected. So if dark matter is real, and the evidence says overwhelmingly that it is, what is it actually made of? This is where the story gets complicated, because we do not know. After nearly a century of searching, after billions of dollars spent on experiments, after some of the most sophisticated detectors ever built by human hands, after theoretical physicists producing thousands of papers proposing candidates, we have not directly detected a single dark matter particle. Not one. But we have a list of suspects. WIMPs, weakly interacting massive particles. For decades, the leading candidate for dark matter has been a hypothetical class of particles called WIMPs, weakly interacting massive particles. The name tells you almost everything. These would be particles with significant mass, somewhere in the range of 10 to 1,000 times the mass of a proton, that interact with ordinary matter only through gravity and the weak nuclear force. Which means they would pass through ordinary matter almost completely unimpeded. Billions of them could be passing through your body right now and you would never feel a thing. No interaction. No signal. Nothing. The reason WIMPs were the leading candidate for so long is that they emerged naturally from a theoretical framework called supersymmetry, an extension of the standard model of particle physics that predicts a heavier partner particle for every particle we already know about. The lightest of these supersymmetric particles would be stable, massive, and weakly interacting, exactly the properties you want in a dark matter candidate. The problem is that the Large Hadron Collider at CERN, the most powerful particle accelerator ever built, has been smashing protons together at energies designed to produce supersymmetric particles for over a decade, and has found nothing. No supersymmetric particles. No WIMPs. No evidence that supersymmetry exists at all at the energy scales we have probed. This has not ruled out WIMPs entirely, but it has made a lot of physicists significantly less confident in them. Axions. A second major candidate is a particle called the axion, originally proposed not to explain dark matter at all but to solve a completely different problem in particle physics called the strong CP problem. Axions would be extraordinarily light, billions of times lighter than an electron, and would interact with ordinary matter so weakly that they make WIMPs look sociable by comparison. But they would be produced in enormous quantities in the early universe and would behave collectively in ways that match what we observe for dark matter remarkably well. Several experiments are currently hunting for axions by looking for the extremely rare occasions when an axion might convert into a photon in a strong magnetic field. So far, nothing confirmed. But the searches are becoming more sensitive every year. Primordial black holes. A third possibility that has gained renewed attention in recent years is that dark matter might not be made of new particles at all. It might be made of black holes. Specifically, primordial black holes. Black holes that formed in the early universe before any stars existed, created by density fluctuations in the first fractions of a second after the Big Bang. These would be black holes ranging from roughly asteroid mass at the small end to tens of solar masses at the larger end, and they would be completely invisible, emitting no significant radiation, detectable only through their gravitational effects. The detection of gravitational waves from merging black holes by LIGO has given this idea new life, because some of the merging black holes detected have masses in ranges that are difficult to explain through conventional stellar evolution. This idea is not confirmed. It is not even the leading hypothesis. But it is taken seriously by serious physicists in a way it was not a decade ago. Sterile neutrinos. And then there are sterile neutrinos. We know neutrinos exist. They are real particles produced in nuclear reactions, including the ones happening in the sun right now. They interact only through the weak force and gravity and pass through ordinary matter almost without interaction. Sterile neutrinos would be heavier versions that interact even more weakly, so weakly they would interact only through gravity. Some observations of X-ray emissions from galaxy clusters have been interpreted as possible signatures of sterile neutrino decay. But the evidence is contested and no detection has been confirmed. The search for dark matter is not passive. Right now, as you watch this, there are experiments running around the world and deep underground, specifically designed to catch dark matter in the act of interacting with ordinary matter. Underground detectors. The most sensitive dark matter detectors in the world are buried deep underground. In a mine shaft in South Dakota, 1,500 meters below the surface, sits an experiment called LUX Zeppelin, a tank containing 10 tons of liquid xenon cooled to extremely low temperatures and surrounded by sensors so sensitive they can detect a single photon of light. It is buried underground to shield it from cosmic rays and background radiation. The rock above it filters out almost everything that could create a false signal. The idea is straightforward. If a dark matter particle, traveling through the Earth as if the planet barely exists, happens to collide with a xenon nucleus, it would produce a tiny flash of light and a small electrical signal. LUX Zeppelin is waiting for exactly that signal. It has been running for years. It has set the most stringent limits ever placed on the interaction strength of WIMPs with ordinary matter. And it has not detected dark matter. Not a confirmed signal. Every null result tightens the constraints, tells us what dark matter cannot be, but does not tell us what it is. Similar experiments are running in Italy under the Gran Sasso Mountain, in Canada under 2 kilometers of rock, in China, in Japan, in Australia. All of them are waiting. All of them are getting more sensitive every year. None of them have found it yet. The Large Hadron Collider. At CERN on the border of Switzerland and France, the Large Hadron Collider accelerates protons to 99.9999991% of the speed of light and smashes them together at energies never before achieved in a laboratory. The hope was that at high enough energies the collisions would produce dark matter particles directly, and their presence would be inferred from the energy that goes missing after each collision. Missing energy, energy that disappears into particles that leave no trace in the detector, has long been considered a potential signature of dark matter. The LHC has seen missing energy events, but none of them have risen to the level of confidence required to claim a discovery. And the absence of supersymmetric particles, the theoretical framework that predicted WIMPs most naturally, has been a significant blow to the most popular dark matter models. Here is where the story takes a genuinely uncomfortable turn. What if dark matter does not exist? What if instead of an invisible substance we cannot detect, our understanding of gravity itself is wrong? This is not a fringe idea. It is a serious scientific hypothesis called modified Newtonian dynamics, or MOND, first proposed by physicist Mordechai Milgram in 1983. The basic idea is this. Newton's law of gravity works extraordinarily well at the scales and accelerations we test it at every day, from falling apples to orbiting satellites to planetary motion. But what if at extremely low accelerations, the kind experienced by stars at the outer edges of galaxies, gravity behaves slightly differently than Newton's equations predict? If you modify the equations of gravity to make gravitational force fall off more slowly at very low accelerations, the galactic rotation curves that Vera Rubin measured fit the observations without any dark matter at all. It sounds appealing, and for explaining galactic rotation curves specifically, MOND actually works surprisingly well. Better than dark matter models in some cases. But here is the problem. MOND fails catastrophically when applied to galaxy clusters. And it cannot naturally explain the bullet cluster, where the gravitational mass and the visible matter separated during a collision. If gravity is modified, why would modified gravity separate from ordinary matter? Modified gravity should follow the mass. The bullet cluster is one of the main reasons most physicists favor dark matter over modified gravity. But MOND has evolved. More sophisticated versions of modified gravity have been developed, including a relativistic version called TeVis and more recently a framework called MOND with dark fields that attempt to address these problems. None of them have succeeded convincingly. But the fact that physicists are still working on them, still taking modified gravity seriously, tells you something important. The dark matter problem is not solved. We are not waiting for confirmation of something we understand. We are genuinely in the dark. No pun intended. Step back from the mystery for a moment and consider what dark matter actually did. Because regardless of what it is made of, its role in the history of the universe is not minor or peripheral. It is foundational. In the early universe, in the first hundreds of millions of years after the Big Bang, ordinary matter was still too hot and too spread out to clump together under its own gravity. The photons of light were constantly pushing the ordinary matter apart, preventing it from condensing into structures. But dark matter does not interact with light. It was not affected by this radiation pressure. So while ordinary matter was being pushed apart, dark matter began to clump together under its own gravity. It formed vast invisible structures, dark matter halos, enormous gravitational wells spread throughout the early universe like a cosmic scaffolding. And when ordinary matter finally cooled enough to escape the pressure of radiation, it fell into those pre-existing dark matter structures. Like water flowing into channels that had already been carved. The dark matter halos became the seeds, the gravitational anchors, around which ordinary matter gathered, condensed, and eventually ignited into stars. Without dark matter forming those structures first, ordinary matter would have been too smooth, too evenly distributed, too resistant to gravitational collapse to ever form galaxies at all. The stars you see when you look at the night sky, every single one of them, formed inside a dark matter halo. Our own Milky Way galaxy sits inside an enormous dark matter structure estimated to extend far beyond the visible disk of stars, a vast invisible sphere of dark matter that the galaxy we live in is embedded within. Dark matter did not just show up after the universe formed. It built the universe. It built the scaffolding that everything else grew on. It is not an add-on to the story of cosmic evolution. It is the foundation. So here is where we actually stand. We know dark matter exists. The evidence from galactic rotation curves, gravitational lensing, the cosmic microwave background, and the bullet cluster is overwhelming and consistent across completely independent measurement methods. We know dark matter makes up approximately 27% of the total energy content of the universe, compared to just 5% for ordinary matter. We know it does not interact with light, which is why we cannot see it. We know it interacts gravitationally, which is how we know it is there. We know it was essential for the formation of every galaxy, every star, and every planet in the observable universe. And we know, after nearly a century of searching, after billions of dollars invested in the most sensitive detectors ever built, that we have absolutely no confirmed idea what it is actually made of. Not one confirmed dark matter particle detected. Not one. The leading theoretical framework, supersymmetry, has produced no confirmed particles at the LHC. The most sensitive underground detectors have set limits so stringent that the most natural WIMP candidates are becoming increasingly constrained. And yet, the evidence for dark matter itself grows stronger with every year. We are in the strange position of being more certain than ever that something is there, and no closer to knowing what it is than we were 50 years ago. This is not a failure of science. This is science being honest about the boundaries of current knowledge. And those boundaries are where the most important work is being done. The next generation of experiments are being designed right now. More sensitive detectors, higher energy colliders, more precise measurements of the cosmic microwave background, space-based observatories that will map the distribution of dark matter across the observable universe with unprecedented precision. We are not giving up. We are getting better tools. And somewhere in the data from one of these experiments, or perhaps from a direction nobody has thought of yet, the answer is waiting. It has been waiting for 100 years. It will not wait forever. In our next video, we go even deeper into the unknown. If dark matter is the invisible scaffolding that built the visible universe, then dark energy is the force that is tearing it all apart. Slowly, inevitably, unstoppably, and we understand it even less than dark matter. If you want to be here for that, you know what to do.